the idea of proximity as similarity, right? We've plotted these points in two-dimensional space, and what we're sort of assuming, what we're sort of hoping is that the data points that are near to each other in two-dimensional space, because they have a similar centroid and a similar loudness, are going to be similar sounds, right? So proximity as similarity, that can be misleading in the way we're choosing our audio analyses. Because if we're choosing spectral centroid, we're trying to summarize an entire spectrum of energy down to a single value. And then on top of that, we're taking the average centroid across a whole slice. So just thinking about mean spectral centroid, we're taking, summarizing a spectrum to one value and then summarizing a time series to one value. And so there's all sorts of pitfalls that you can run into there. They're important to reflect on and think about as you're doing your audio analysis and your data analysis here. There's another step that it can be a pitfall that we have to think about, and that's sort of in this data domain when we consider proximity as similarity. If we think about our data space as a two-dimensional, Euclidean distance space, like a city grid, for example, and we want to find the distance between 2 points, let's say this point and this point, the way that we would compute that is we would find the distance between the 2 points in one dimension. And in this case, if we're looking at decibels, there might be a range of about 100 decibels. That would be the biggest range we would probably find in a data set of sound slices. And then we would also find the distance between the 2 points in the other dimension. And if we're thinking about spectral centroids, we might find a range of about 10,000 hertz or so. And then what we would do is we would find the hypotenuse of this triangle, find the line that connects the 2 points. We'd use the Pythagorean theorem to compute that, and that would be our distance between these 2 points. Now, if you notice, one of our analysis dimensions is 2 orders of magnitude larger than the other, which means that the distance between these 2 points is going to be much more greatly influenced by this dimension than it will be by this dimension. You can imagine if we were to cut this dimension in half, the distance of this orange line would change quite a lot. If we were to double this dimension, the distance of this orange line would change quite a lot. If we were to cut the distance of this dimension in half or double it, the distance of this orange line wouldn't change very much. And so the dimension that has a much larger range is going to have a much larger influence on the distance between the data points as we compute them. And any dimensions that have a much smaller range will have a much smaller influence. Now, this might be desirable. Maybe we want, spectral centroid to be 100 times more important in our distance computation than our loudness value. But this is usually not the case. And if we are doing something like that, we have very specific choices about why we're making those decisions. Usually what we're going to want to do is we're going to want to scale the data so that all of the dimensions involved, in this case, we just have the 2 dimensions, but all of the dimensions involved will have a relatively similar impact on our distance computation. The way that we do that is we're going to find the full range of the centroid values from the smallest to the biggest centroid, the full range of the loudness values from the smallest to the largest loudness value. And we're going to scale the data so the minimum and maximum will now be between 0 and 1. And this process is called normalization. And so normalizing is what we have been doing, where we convert all the ranges of all the dimensions to be between 0 and 1. There are other types of scalars that we'll look at in a moment. And on the way there, let's also consider how these different scalars will change the way that our data set looks to us and looks to these data algorithms. So here I have spectral centroid and loudness. Here are the drum hits, and we can see that we're looking at a spectral centroid from 0 to 10,000, and we're looking at loudness values from -5,000 to 5,000. So a range of 10,000 in both dimensions. Now, of course, this doesn't really make sense, but here we're just looking at the raw data. If 1 hertz equaled 1 decibel, and this is, if we don't do any scaling, this is actually how the data will look to these data algorithms, like the KD tree or like the dimensionality reduction algorithms we'll look at shortly. And that's because those algorithms, they don't know that one dimension is hertz and one dimension is decibels. They don't know that one dimension has a smaller range and the other dimension has a bigger range, etc. So we'll look at, for example, this slice number 27 and its nearest neighbor happens to be slice 21. And if we zoom in a little bit, so now we're looking at about 1,000 units in each dimension, we can see that the nearest slice is going to be between slice 27 and is going to be slice 21. But you can also notice that because of the way the data is structured, the nearest point is pretty much always going to be whatever point is like next along the line, because these points are basically on a line from left to right. And so the nearest point to any other point is going to be whatever it's next to it on the line. If we normalize this data, now we have all of our points organized in space between 0 and 1. And if we check slice 27 and compare it to slice 21, that is clearly no longer the nearest neighbor, right? That is a much farther distance in this normalized space. In fact, now the nearest slice to slice 27 is slice 13. So by normalizing the data, we now are changing the relationship between the data points in their distance computations and making sure that our spectrocentroid and our loudness are equally weighted in how we're considering the distance as similarity, proximity as similarity, how we're measuring similarity between these slices. Another type of scalar that we have in FluCoMa is called standardization. And what standardization will do is it will analyze the data set and so that each column of data will end up having a mean of 0 and a standard deviation of 1. And what this does is it centers the data around 0. So roughly half, this is not exactly what it's doing, but roughly half of the data will end up having a positive value, roughly half of the data will end up having a negative value. And then also it tries to scale the data around 0 so that a lot of the data will fall between the -1 and 1 range. And it does this in both dimensions. And this, again, is about scaling the data so all of the dimensions are in a similar range, this sort of -1 to 1 roughly range that we get from standardization. Now, if we were to analyze our data points, slice 27 does not have slice 21 as its closest data point. It also does not have slice 13 as its closest data point, which was the nearest neighbor when we normalized. When we standardized, the nearest neighbor to slice 27 is actually slice 23. And so you can see how even the difference between normalization and standardization can produce different nearest neighbors, and therefore different distance calculations, and therefore also is going to give us different results when we use this data in our data analysis algorithms. There's one more scalar that we have in FluCoMa, and that is called the robust scale. And what the robust scalar does is it analyzes each column of data, finds the median value, which is going to be right in the middle of the data, and makes that value 0. So what the robust scale does is it will make half of the data be below 0 and half of the data be above 0. And the median value will be right on 0. And then it also analyzes for the 25th and 75th percentile, and then adjusts the data so that the distance between the 25th percentile of the data and the 75th percentile of the data is a range of 1. And what this means is that 50% of the data between the bottom 25% of the data and the top 25% of the data, the middle 50% of the data will have a range of 1. And we can see that that is what these dotted lines are here. From here to here represents 50% of the data points in the X dimension. And from here to here represents 50% of the data points in the Y dimension. And that also means that 25% of the data is above this line and 25% of the data is below this line. 25% of the data to the left of this line, 25% of the data to the right of this line, and therefore 50% of the data in between. So that's what robust scale does. And there are reasons why you might want to use any one of these scalars. Normalization is definitely the most straightforward, the most simple, and it ensures our outer bounds. It ensures that the values will always be between 0 and 1. So that might be an interesting, useful thing to do. Standardization is useful because it gets the data around 0 and then sort of scales it roughly between -1 and 1. There are some statistical properties that you could look up on the FluCoMa Learn site about more specifically about what that means, but it gets the data around -1 to 1, and that could be useful for us to have most of the data in that smaller range, but not necessarily clamp it to a 0 to 1 range if we didn't want to do that. The thing about standardization is that it is using the average. And so if we have some crazy outlier that's a really huge number way outside the rest of the data, that number might skew the average, right? It'll bring that average way away from a lot of the rest of the data in the data set. So that could be a problem that standardization could have. Robust scale, because it's using the median and only percentiles of the data, it actually is going to be more robust to outliers. So it will ensure that 25% of the data is above this dotted line. And if one of the data points is a massive outlier that's way out there, way different from the other data points, robust scale actually won't even know or won't even care, because it's just saying 25% of the data should be to the right of this dotted line, even if that data is like a really massively different than the rest of the data, a really big outlier. And so these are sort of some of the ways of thinking about how you might use, why you might use these different scalars. And there will be times when you might think, oh, wow, I have some really big outliers in this data. Let me see if robust scale is helpful. Or I really need to make sure that my values are between 0 and 1, maybe because I'm using the sigmoid activation function. And so I'd want to use normalization. And also when we're doing the distance computations, like with the KD tree or with concatenative synthesis, it also can be useful just to try different scalars. Let me just see, what does my sound space end up feeling like, or what does my concatenative synthesis end up sounding like if I use normalization? What does it end up sounding like if I use standardization, robust scale? So it's actually useful to switch between the different scalars and just kind of see how they change the sound result. And so that's a nice way of thinking about scalars in FluCoMa, just preparing yourself to try all of them out.